Welcome back to Codex. Our speaker today is Abiy Tasissa from Tufts University. Professor Tasissa is an expert in the mathematics of data science. Today, he'll tell us about multidimensional scaling. Take it away, Abiy.
Thank you for the kind invitation. So today I will talk about dual-based approach to classical multidimensional scaling. This is a work of my student, Samuel Lichtenberg, who finished his master thesis last year. So I'll start with some motivation for why we study this problem. So here is an example for one application of multidimensional scaling. In this particular case, this is a structure prediction problem. We have the original structure that's shown in green, and we have the red and the blue, which are the actual structure and the estimated structure. Okay, so the goal is in protein structure prediction, we get measurements from NMR, nuclear magnetic resonance spectroscopy, or X-ray diffraction. We have some of the distances between the atoms, and the goal is to leverage these distances to be able to predict the 3D structure of the overall protein from the limited distance measurements that we have. Here is another motivation. Here we have the sensor localization problem. In this particular example, which is just a stylistic example, we have 4 sensors, so located at X1, X2, X3, X4. But the information we have is that whenever the sensors communicate, we have the pairwise distance between them. So we know the distance in this case between X1, X2, X2, X3, and X1 and X3, and X2 and X4. But we don't know the distance between X1 and X4. Maybe because of geography, or maybe it's very expensive to have these 2 sensors communicate. And the idea in sensor localization is, given the distances that we know where a few of these sensors communicate, could we locate or predict the location of the other sensors? Okay, so the input to this problem is the distances. Okay, so in many applications, we could have distances missing for various factors. For example, in the first example I gave was a structure prediction problem, the distances could be missing because we can only measure the distance between 2 atoms when the atoms are close to each other. That typical range for protein structure prediction is typically 6 angstroms, or it could be quite expensive to compute all the distances, like the sensor localization problem, where we wanted, if we wanted all the sensors to be able to communicate their distances. And secondly, in many applications for analysis or visualization, we would like to get from the points, from the distance matrix, we'd like to get points that approximately or exactly realize this distance matrix. Okay, so this problem is called the distance geometry problem. It has been quite studied, and there are a lot of applications to it. Okay, so in today's talk, at least for the majority of the part, I'll be focusing on the classical multidimensional scaling, which can be seen as one instance of the distance geometry problem where we have all the distances. Okay, so let's consider the setup. So we have n points, so P1 to Pn, and these points live in some r-dimensional Euclidean space. And for now, we start by defining the squared Euclidean distance matrix D. Okay, so how do we define the squared Euclidean distance matrix D? The squared Euclidean distance matrix D is given simply by this formula. And in fact, we can write this distance matrix D compactly in the following way. Okay, so this D is a square distance matrix. And if we write it this way, we can see that there is a certain relationship that emerges, and that's that this D depends on this matrix PP transpose. Okay, so this PP transpose matrix is known as the Gram matrix. Okay, in other words, if we define this Gram matrix X here, then each entry of the square distance matrix, Dij, can be related to the Gram matrix in the following way. So the point I want to emphasize here is that if we know the gram matrix X, then we have a way to go to the points. Okay, so the idea of in the first part of the talk is I'll argue that we can go from the square matrix D to X, and once we go to X, we can go to P because X is related to P directly. So the question that we'd like to ask is, if I give you the full distance matrix, meaning that we have this square distance matrix D, can we find the configuration of the points P? Can we find P1 to Pn? And this is essentially the classical multidimensional scaling problem. Okay, so let's note a few facts about this problem, some properties of this problem. First, one can show that by using basic rank inequality, the rank of D is at most R plus 2, the rank of the square distance matrix, and the rank of the gram matrix is R. Why is this nice? Because irrespective of the number of points we have, if we have n much greater than R, both the gram matrix and the square distance matrix are low rank matrices, and this property is typically leveraged in optimization problems by imposing low rankness on the D and X that we want to reconstruct. Okay. Now, we are given this full distance matrix D, and our goal is to get X first. Okay, so I'll show that we can go from D to X, and then once we go from the distance matrix to the gram matrix, then we can go from the gram matrix to the points. Okay, and that will be the idea of the classical multidimensional scaling problem. Okay, so let's recall once again how the square distance matrix is related to the points. So each dij square has this form. So there are two ways to get to the result that I'm going to show here. So I'm going to show the one which is based on the linear algebra formulation. Okay, so the first thing is, let's sum over the index I. Okay, so I'm just going to sum this expression on both sides over the index I. Okay, so we get the following expression. Okay, the following expression. I do the same thing, except I sum up over the index j. And finally, I sum over both the index I and over the index j. And you might see that I have carefully highlighted the red terms. So these are the red terms. And my goal is to get this pj square, pi square. And if you look at these terms, these are the summations over I of the norm of pi square, the summation over j pj square. So since the indices are dummy, these are quite the same expression. And the last expression allows us to get a closed form of this term in terms of the distances. So once again, our goal is to relate the distances, map the distances to the gram matrix. So what I'm going to do in the next slide is actually take this expression and plug it here and here and get an expression for pj square and pi square. Okay. And if I do that, so I get an expression for pj square and I get an expression for pi square. Okay. Now, we know that the gram matrix, by definition, the entry of the gram matrix is pi transpose pj. And another way to write that is by pi square plus pj square minus dij square. Okay, so I'm using the fact that each entry of the gram matrix can be written this way. And by using these two expressions, now I have expressed everything in terms of the distance matrix. Okay, so this is the main goal. So I have expressed my pj in terms of the distances. I have expressed my pi in terms of the distances. And now I have this formula, which tells me that an entry of the gram matrix can be fully expressed in terms of the distances. Okay, so if I clean up everything and do the algebra, I get this expression. An entry of the gram matrix can be written as the inner product of pi transpose pj. And by the work we have done in the previous slides, we can write this way. Okay, so I'd like to pause here and sort of emphasize what we have done. What we have done is that we have managed to write an entry of the gram matrix purely on quantities that depend only on the distances, which is what we are given as input. Okay. Of course, now that we have written each entry of the gram matrix, our goal is to say, can we write the gram matrix compactly as a function of the square distance matrix? And the answer is yes. So if I write the full gram matrix, the full gram matrix X can be written as minus a half J times dj. And this J matrix right here that you see is called the centering matrix. So this is identity minus 1 over n, the 1 matrix. And what we have shown is that if you give me the square distance matrix, I can map you to the gram matrix by using this formula. Okay, so this J is called the centering matrix. Okay, so this is a classic result, which essentially says the following. If I give you a distance matrix D, how do we know that this is a valid Euclidean distance matrix? And this result due to Schoenberg essentially says the following. D is a squared Euclidean distance matrix if and only if we apply this operator, minus half J dj on both sides. If I apply this matrix is positive semi-definite. Okay, and this matrix that we have, this J, is called the centering matrix. Okay, so with that, the classical multidimensional scaling algorithm, or CMDS, proceeds as follows. The input is D and R. Okay, so I'll give you a full distance matrix, square distance matrix D and R, where R is the target dimension for the points. We first compute the gram matrix, okay, by using this formula that we have derived also from the Schoenberg characterization. And now that we have the gram matrix, we remember that the gram matrix is PP transpose. So to obtain the gram matrix, since the gram matrix is symmetric and positive semi-definite, we can do a spectral decomposition or eigenvalue decomposition, and we can take the square root. Okay. So maybe let me pause here and see if anybody has any questions before we go to the second part of the talk. Was there something in the chat? Okay. So this basically shows the classical multidimensional scaling algorithm. I would like to sort of explain why we get this formula or this formulation. Why is it that when we apply this J operator on both sides of the square distance matrix D, we get the gram matrix? Okay, and the perspective is as follows. Let's define this T, this curly T, to be the subspace of Rn that's spanned by the constant vector. For example, a vector of ones. Now, if we look at this centering matrix, this centering matrix is nothing but the operator that orthogonally projects onto the complement of this T. So we have a space that's spanned by the constant vector, and the projection onto the orthogonal complement of that space is this J. And if we recall the form of D, we'll notice that the first two terms are rank 1 matrices. So when I apply this J operator on both sides, it basically removes these two terms. This J operator is basically projecting me into the orthogonal complement of the space spanned by the constant vector. So finally, up to scaling, we basically have applied J on both sides of these, which gives us the gram matrix of the set of points centered at the origin. So here is sort of one slide of like what's really happening with this J operator mapping us back to the gram matrix. Okay. So this sort of concludes the first part of the talk, which is, what's the classical multidimensional scaling algorithm. And essentially the main summary is that if we have a full distance matrix D, you can apply this centering map on both sides and minus a half, and you get the gram matrix. Once you get the gram matrix is defined precisely in terms of the points. So you could do eigendecomposition to be able to recover the points, and the points are going to be unique up to rigid motion. Okay, so now I'm going to talk about one of our contributions, which is how do we do a dual-based approach to classical MDS. Okay, so first I'll do some discussion of the setup. So we have two matrices A and B. If we are given two matrices A and B, this will denote the trace inner product. From now on, this L will denote n times n minus 1 over 2. So these are basically the number of distances in the upper half of the distance matrix. And we basically account for symmetry, and we don't care about I is equal to j in the distance matrix. So our universal set will be the collection of ij for which this inequality holds. And finally, we consider the set of symmetric matrices whose row sum is 0. And just to show why this is the case, the matrix that we get by default, because of the way we centered our points, this J centers our points at the origin. So the solution we get, the gram matrix we get from classical MDS, will always have its points centered at the origin. So X times the 1 vector is the 0 vector. Okay. So this is a space that we are interested in. And we can conclude that if I have an X in this set, I can expand it in this way, where V alpha is the dual basis of W alpha. And the question is now, what are these W alpha and V alpha? Okay, so I have set of symmetric matrices whose row sums are 0. I can expand it in a dual basis expansion, and I want to find what are my W alpha and V alpha. Okay, so here is how the W alphas look like. So if I have an alpha index, which is defined in terms of alpha 1 and alpha 2, W alpha is given by this formula, where Eij is the standard matrix where we put a 1 in the ij's position. Okay, so this is a matrix of zeros except at the alpha 1 position, alpha 2 position, alpha 1 alpha 2 position, and alpha 2 alpha 1 position. Now, a very important quantity when we use this for analyzing optimization algorithms for the distance geometry problem is this matrix H. So this matrix H is the correlation matrix or the inner product matrix. So the alpha beta entry of this matrix is the trace inner product between this measurement basis W alpha. Okay. And how do we find our dual basis? The dual basis is given by the standard formula. So to get the dual basis V alpha, I can apply this formula. Okay. And we can easily verify that if I do the inner product of V alpha and W beta, that's going to be, the Kronecker of alpha beta. So it's only going to be 1 when this alpha and beta index are exactly the same. Okay. So this is the standard dual basis formulation. My goal is to now visualize or understand what this W alpha and V alpha look like. Okay, so let's do an example. So this is when n is equal to 4, just to illustrate what this W, V, H, and H inverse look like. So W12 is E11, E22, E12, and E21. So essentially, W alpha 1, alpha 2, it puts 1, 1 in the alpha 1, alpha 1, and alpha 2, alpha 2, and a -1 at these entries. And this is how the matrix V12 looks like. And here is our H. So when n is 4, this is a 6 by 6 matrix. And here is the structure of H. And here is the structure of H inverse. Okay. So when we did the analysis for, when we looked at this matrix H, irrespective of the dimension of n, it had a very nice and appealing structure. And the first part of this was to establish that more rigorously. Okay, so irrespective of n, this matrix H has a very nice and appealing structure. Same with this V alphas, the dual basis. And in the coming slides, I'll explain why that's the case. Okay, so if I have a gram matrix, which is sort of the most important objects that encodes the point information, it can be expanded. It can be expanded in the dual basis in this way. Now, let's take a look at actually the coefficients. So what are the coefficients? We have already derived W alpha in the previous slide. So if we do these coefficients, so if we apply this formula, we see that this is nothing by our earlier observation that xii plus xjj minus 2xij gives us a distance square. These coefficients are nothing but the distance square. So another way to think of the classical MDS is we are taking our gram matrix, using our distances as the weights, and combining them using the V alpha. Okay, so the gram matrix, the centered gram matrix, is nothing but a linear combination of these V alpha matrices, and the weights are the distances. Okay. For this to be useful, it will be nice to know what this V alpha is and what are the spectrum of these matrices that appear in this formula. Okay, so what's the spectrum of this matrix H, and can we write this V alpha explicitly? Okay, so let's recall once again what H is. So H is this matrix, which is size L by L, and it's the inner product matrix. So it means that the alpha beta entry of H is the inner product between W alpha and W beta. It can be easily verified that H is a symmetric and positive definite matrix. And you recall a few slides before what this W alphas look like, we can easily find what the inner product between a pair of these base vectors W alphas looks like. Okay, so if I go here and look at this, if the two indices are exactly the same, then we get a 4. That's the inner product. If they share at least one index, we get a 1. And if this index and this index don't intersect at all, it's a 0. So H only has 3 distinct entries. On the diagonals, it has a 4. And the off-diagonal elements are either 1 or 0. It's 1 whenever these indices share at least one common element. And if these are completely disjoint, then it's 0. So for example, if I do W12 and W45, that's going to be 0. Now, irrespective of the dimension, if you do numerical experimentation, you see that H only has 3 distinct eigenvalues, 2, n, and 2n. And this is true irrespective of the dimension. And our goal is to understand why that's the case. Okay. So to do that, let me first describe what's called a triangular graph. So the triangular graph can be formed from the complete graph on n vertices, which I'm denoting here by Kn. And here is how the triangular graph is going to be formed. Every time we have an edge Eij in Kn, we add a vertex Vij in our triangular graph. Okay, so each edge in the complete graph maps to a vertex in the triangular graph. And 2 vertices of the triangular graph, we'll connect them, Vij and Vkl, if the edges share a common vertex in the complete graph. Okay, so just one more time. So we take the complete graph and we form this triangular graph. We add a vertex for each edge Eij in the complete graph, and 2 vertices in the triangular graph share an edge if these 2, the corresponding vertices, share a common vertex in the complete graph. Now, here is the nice thing. So as I said earlier, this matrix H has a 4 on the diagonal. So we can take that part out. So we can take 4 times identity. And the remaining part, as we noted earlier, is either a 0 or a 1 once we remove the identity part, right? And that is nothing but the adjacency matrix of a particular triangular graph. So the sketch of the proof is actually quite simple. Now, rather than thinking of these W alphas and W betas as matrices, we sort of think of them as nodes. So if I define my vertices of Kane to be the points and my edges with the base vector W alpha, and if I apply the definition of my triangular graph, then we basically get that the remaining matrix is nothing but the adjacency matrix of the triangular graph. Okay. Now you might say, why is this formulation useful? These have been quite studied. Then we can automatically get the spectrum of this H matrix quite easily. So basically, the inner product matrix has these 3 distinct eigenvalues with this multiplicity. And this is a classic result due to Hoffman, which basically characterizes any spectrum of the adjacency matrix of these triangular graphs. Okay. So now that we have completely characterized the spectrum of H, the next question is, what about the dual basis formulation? So what about this V alpha? Of course, we already know V alpha because V alpha is given by this formula, but in numerical implementations or optimization algorithms, this is not quite easy for analysis or computation. So we would like to understand what this V alpha actually looks like. I'll not go through the proof, but in fact, the V alpha has a very simple dyadic form. So the V alphas we have a closed form formula for this V alpha, which is given by this. And recall that this J is our centering matrix. So this is the I's column of J, and this is the J's column of the centering matrix. So essentially, we have a closed form for this matrix V alpha. Okay. We might be interested what kind of properties that V alpha have. In fact, V alpha is a rank 2 matrix. And we can completely characterize the non-zero eigenvalues. These are the non-zero eigenvalues with this corresponding eigenvectors. And this is true irrespective of dimension. So what we have shown is that the X matrix that I have, the X matrix in the Gram matrix can actually be expanded as a linear combination of this V alpha. And we know what these building blocks look like. We know exactly what this V alpha looks like. Further, we know exactly what the spectrum of this looks like by associating it to the triangular graph. Okay. And once we have this, we can ask the same question that we have asked earlier. If you give me distances Dij, collection of valid Euclidean distances, and if I expand it using my dual basis, that gives me a valid Gram matrix. Okay. So in practice, our distances contain some measurement errors. So for this one, let's assume that our distance matrix is corrupted with some additive noise, and we obtain d tilde. So I'm going to call that matrix d noisy. So d noisy is d plus d tilde. So the Gram matrix, the true Gram matrix corresponding to d, I'm going to call it x. And the Gram matrix corresponding to d noisy, I'm going to call it x bar. And because now we have computed all of these quantities explicitly and we understand the spectrum, we can control this type of things. I'm giving this as an example, but we can actually do it with other norms too, because we have an explicit characterization of what these V's look like and the spectrum of H. So in this case, we can actually show that the largest entry of this in absolute value can be bounded by 4 times the perturbation, the largest perturbation in absolute value. Okay. So this allows us, whenever distance matrices are perturbed, then it will allow us to see by how much are the gram matrices perturbed. Okay. What was interesting was we did this problem in the context of distance geometry, and we found connections to a related problem in metric nearness. So I'll introduce, this is a tangential problem called matrix nearness, and I'll introduce what that problem is and what the connection is. Okay, so just first few to set up the notation. So I'm going to use this dn to denote the set of dissimilarity matrices. So by dissimilarity, I mean matrices which are non-negative, symmetric with zero diagonal. And then I'm going to use this curly mn to denote the set of distance matrices. So these are matrices which satisfy triangle inequality. Okay, so that's the only requirement. So we matrices that satisfy triangle inequality. So in a couple of papers, people are interested in this metric nearness problem, which is I give you some weight matrix, and I give you an input matrix D. Okay, and the question is, can you find the nearest valid distance matrix A? Okay, so formally, the problem looks like as follows. I give you D, some weight matrix, and the goal is to say, can we find the nearest X, which is a valid metric, a nearest valid distance matrix that minimizes this objective. And in the paper, in this set of papers, they consider different norms, and in the different norms, you have different solutions. Now, if you look at one of the original papers that suggested this, they have a very tall matrix A that sort of encodes the constraint for triangle inequality, because a very important part of this matrix nearness problem is that this M, this object that you are seeking for, has to satisfy the triangle inequality. Okay, so this A matrix has quite big matrix. It has this number of rows and this number of columns. Okay, so each column represents a distance between 2 points, and each row will represent a triangle inequality constraint if I have 3 distances. So any of the triangle inequality constraints can be formulated in this way, right? We can always rewrite them in this way. And the entries of this matrix are the sign of each distance in this particular inequality. Okay, so to make this concrete, I'll illustrate this with an example, and that will make it quite easier to see what I mean. So let's consider 4 points, P1, P2, P3, and P4. Okay, so I'm going to label my distances as Pi, Pj. Okay, so this is the distance Dij. And when we look at this inequality, I'm going to write it as Pi, Pk, Pj. So the first 2 points, these first 2 points in this list refer to the index of D with a positive sign in the inequality. In this case, the one which has a positive sign in front of it is the Dik. So these 2 points are the ones corresponding to that. Okay, so this is just a convention. And here is just, I've abbreviated the distance matrix because it's 18 by 6 for the case of 4 points. But essentially, this is what the matrix A looks like. Okay, so this is the matrix that encodes the triangle inequality with the 4 points. And this is quite central to the optimization algorithm proposed in the metric nearness problem. In this paper, the authors make the following observation. So they say that A has 3 distinct singular values. So these are the singular values. And they also note that these are the multiplicities. Okay. And it was quite interesting to me because this is quite the same pattern that we saw in the H matrix earlier. So we're quite curious if that H matrix is actually connected to this A matrix in the matrix nearness problem. So the A matrix, which is basically the matrix that encodes the triangle inequality. And in fact, the answer is true. It turns out this matrix A that arises in metric nearness. So, and the H matrix, which is the inner product matrix of this W alphas that I showed you earlier, are identical up to diagonal scaling. So A transpose A and this minus H are identical. In particular, the result of this theorem shows that A transpose A can be explicitly written in this way. And since we have already characterized the eigenvalues of the spectrum of H, by a simple shift of the identity, we can now characterize all the eigenvalues of A transpose A, which are the singular values. It's still not clear to me why these two matrices have quite the same property, because one is appearing in the metric nearness problem, one is in the dual-based approach to multidimensional scaling, but there seems to be some underlying connection for why this same type of object arises in both problems. Yeah. The next question was, how do these results change? And this is a question not only in the theory sense, but also in the computational sense, in the distance geometry problem that I mentioned earlier. How do these results change if we change the centering? So let me remind you sort of where we started. When we did the classical MDS problem, we had this J matrix. And this J matrix, let's recall, is this centering matrix. And what it does in the conventional formulation is that it takes a set of points and centers you at the origin. So it shifts the points so that the center is at the origin. Now, of course, there is nothing special about the origin. So the natural question is, how does the spectrum of everything, how does the properties change if we allow the centering to be not at the origin, but at a different point? Okay, so if we go to, and this was studied by Gaur in a set of two papers in 1982 and 95. So much like the result we saw earlier, there is a generalization if you allow for a centering. So for any vector S that sums up to 1, then you can relate the distance matrix to a gram matrix in this fashion, and that will, this S will be a different centering parameter. So the standard one, if you remember, the one we did earlier was when S was 1 over n to n. So that was the earlier vector we had was S is equal to 1 over n times n, which will take us to the standard classical MDS formulation. But in practice, there is no restriction about this S. As long as this is a vector S that sums up to 1, we can relate the distance, the square distance matrix to the gram matrix. Okay. Following the same analysis that I have done earlier, we can actually now also develop the dual-based approach for this. So there is a lot of notations here, but the main idea is that now, earlier we were saying that these are centered gram matrices, meaning x times 1 is the 0 vector, but now this S could be anything. The points don't have to be centered at the origin, and we can derive what the measurement basis, the W's, look like. Now the W alphas have this form where this A is given here. In the constant case, this boils down to the standard W alpha that we have developed earlier. And much like the W alphas, we are also interested in what happens to the dual bases. Okay? And we can also characterize the dual bases. Okay, so we still have that nice dyadic form that carries even when the points are not supposed to be centered at the origin. Okay. Now here is some of the questions we are currently looking into. We don't have answers for this, and I'll be happy to hear any thoughts or any questions or discussions on this. So initially what we had was we had this H matrix, and we defined this inner product matrix. Now the question is, how does that change when we do the centering? The earlier matrix H we had is very nicely structured with very nice spectrum. And we're able to show there is a regularity in it. We're able to connect it to triangular graphs and be able to find all the spectrum. But the question is, how does that change when you do the centering? And we don't have a good answer for this right now. It seems like the centering does affect the spectrum quite significantly for this H tilde. And when we do this in the optimization, one would expect that the centering shouldn't matter, in the sense that if we go back to our dual basis formulation here, if I give you only a few of these distances, right here, d alpha, and I ask you, could you give me an estimate of X? And if we formulate one optimization algorithm based on the distance geometry problem, we'd imagine that the centering shouldn't really affect that optimization problem. But that doesn't seem to be the case, in fact, because the W alphas and V alphas and the spectrum do change. So any theoretical guarantees for the optimization algorithm hinge on what H tilde is. It's a little bit contradictory to me, because one would like to have a complete theory for everything that doesn't seem to be sensitive or depend on the choice of centering. But these things show up in the spectrum, and these things dictate how well optimization algorithms work, to what extent they recover the underlying structure when you don't have all the distances. So the current work is to leveraging this for analysis of optimization and exploring its connection to the Euclidean distance geometry problem. So the presentation is based on the following, 3 papers. The first paper was the one where we had the motivations, but we were not able to. We had the numerical observation for H and V alpha, but we didn't have the precise proofs. So in the second paper, we basically show all the results that I discussed in this paper. And the third paper, we leverage the fact that we can define the center anywhere, and the dual basis can be extended to any centering, and apply it to the Nystrom problem, related problem in distance geometry. And this work is supported by NSF grant, and I acknowledge the support. So thank you.
All right. Thanks so much. As usual, I'm going to encourage everyone to smash that reaction button. Show Abiy our appreciation for a great talk. Are there any questions out there?